So, as we saw, Daniel Kropp was blocked in Paris because he's sick. He really wanted to come here, but unfortunately it was not possible. And just 2 days ago, he asked me to replace. So I will try to perform all this presentation was prepared by Daniel from 2 months ago. So for the people who don't know who Daniel Kropp is, use a short introduction. He's a very well-known system engineering expert worldwide. As you know, we have INCOSI organization that is driving system engineering methodologies and standards. And Daniel is one of the INCOSI fellow. So we have only 60 INCOSI fellow in the world, and only one French, who is Daniel. So it's quite top recognition. He's also in charge of École Polytechnique System Engineering Chair for 20 years, in collaboration with Thales, DGA, and so on. And he is the president of Sesams. Sesams is a consulting company we work with for already 4 years, specialized in system engineering consulting, transformation consulting. So they are working on companies' architecture, and they are working on system engineering architecture with very good references in Europe, in US, and in Asia, where we started 2 years ago working mainly in Japan, in China, and Singapore. So we'll have an overview about system engineering, where it's coming from. Just explain 2 original examples that push to this approach. The first one is the European launchers, was built between Germany, France, and UK. And is from the 60s, and they lose 6 tries to launch this launcher that was failed. And the reason, the only one reason was the integration between the teams. So they check the work done by Germans, by French, by UK. All the work was perfect. But when they put all these systems together, we have a lot of problems on the integration because of the complexity. Another example is French submarines in the 70s. It's similar, it's within France. We have 2 different entities. We have the submarine and we have the air controls, and they lack to make the correct integration because of the integration of both systems. So the first missiles crash because of the integration. So this is 2 examples coming from almost 40 years ago. And what is important here is that these examples are, we have this example of systems that are not working because complexity and integration. So even if it is coming from aerospace and defense, today we find all these problems in other industries. For example, in transport and mobility, because all the vehicles become more and more complex with more and more electrical systems. And the approach that we use to solve this aerospace and defense complexity is something that we are doing today also with many other industries. So how to solve that? The first way is formalize the systems. So it means we will formalize who are the stakeholders, we will formalize the life cycle, we will formalize the functional architecture, the components. And the fact that we formalize all these different entities is a way to simplify the complexity. So we are not managing all the complexity together, but we are isolating the complexity into different areas. Another one is with a new role, system architect. So it's a new role, it's coming from system engineering approach. When we want to make it work at company level, we need this kind of profiles. And it's something that has been developed strongly, for example, in PSA, one of our model-based system engineering PLM success story, where they hire a lot of system architects to manage the functional and services layers. Another example of problem of complexity and integration is Calcutta Subway. So Calcutta Subway is a new subway, very high-tech, very modern, that was built recently. And they have some problems because the driver was managing the train with a touch screen. And the first summer of operation of the subway, everything was blocked. So the touch screen was white, it was not working, the subway was stopped, and Calcutta city was completely in a chaos. For sure, they take this component, they test, and the touch screen is perfectly working. So they take several days, several weeks to understand what is going wrong. And the reason was that the different teams working together, they didn't have a global view what they was working, what they was developing. So what happened is that it was summer, plus 45 degrees Celsius. The brakes was too much hot, so the control system tried to reduce the temperature. And the way to reduce the temperature is that they make the bus communication absolutely busy at the limit that the touch screen was not working. So they spent several weeks to discover this issue. And again, it's something that's a side effect because of the integration of complex systems. The solution, we will see later, is introduce operational layers. So as we explained before, we try to simplify the problem. So to simplify the problem is also to have a clear specification of the system shared by all the people working on the system. And the way to do that is with operational layers architecture, where we will identify all the stakeholders and all the different use cases of the system. Another example, this one from the 80s, from French OM Automotive, is the creation of a new depollution function. So they want to make a depollution function, and they have two components that are unpacked by this function. The first one is the powertrain team, and the second one is the people in charge of the chassis. They spent 5 years. It didn't work at the end very well, and they have an overcost of more than 5 million euros. The reason was that nobody was in charge of the function. So nobody was in charge of the global view of the integration. So to solve it, beside the operational layer we saw before, in system engineering approach, we introduce a functional layer. This functional layer is transversal and is independent of the implementation. It is again what has been done in PSA. We have teams in charge of transversal functions. And it's very important because we can capitalize and we make very, very fast updates of the system. So we have the same functional architecture, no matter, for example, if we are working with thermic engines or we are working with electrical ones. So we save a lot of engineering rework. If we think about transport and mobility, as we explained previously, system engineering was pushed 50 years ago by aerospace and defense. Today is something we can find in many, many industries because we have a lot of complexity, we have a lot of electronics in many industries. And one example is transport and mobility, where we have new trends on the market, like ADAS, like autonomous vehicle, which request a lot of components. Every component has a lot of interfaces, and because of that, the complexity is extremely, extremely high. So to manage this complexity, we try to reduce the problem into different layers. This is the basis of system engineering methodology. I will not go deep because this is very, very, we can spend hours. But we say that we think about what are the needs of the system. We check what is the functions of the system inside, and then we will check how to implement it. So these three layers helps to simplify the complexity and to manage the complexity in a better way. Here, what we can see is, in fact, it is PSA. What we can see here is PSA organization. We have here 15,000 people aligned with previous pyramid. So one of the outcomes of PSA transformation was this new architecture, organization company. Every box is a team. It can be from 2, 3 people to 200, 300 people. And we find the service and the functions. We can see its transversal teams in charge of different components. In the blue one, we can see the component engineering, traditional engineering. And it's quite interesting because we can see also when they are working in components that are not high value for the OEM, they stop very high the design and they send to the supplier. And if it is very important from IP point of view, they go till the component part. And in this architecture, we try to implement the methodology. So it means one service or domain is one responsible. It's a side effect of the implementation of model-based system engineering in PSA. Second solution is a framework. So this organization is aligned with the methodology, and the methodology is an implementation of the framework. So we talk about framework because we don't have a methodology ready to use. It means every customer is different, every need is different, and we need to adapt to every customer. For example, we have a customer from government ministry for defense. They will focus mainly on operational layer. They don't care about the next ones. We have companies from aerospace. They will focus a lot in behavior, dynamic behaviors. From automotive, maybe they will focus a lot on function, service, and static views. So this methodology is something that we need to adapt to every company and to every customer. And just before finish, key success factors we capitalize from PSA. So PSA was 3-4 years of PLM, model-based system engineering transformation. And here we have the feedback from CESAMs about how to make this kind of project successful. So the first one is to be sure we have a top executive sponsor. In this case, was this sponsor who pushed for system engineering. Why? Because in 2013, he worried a little bit because for him the PLM adoption was key to be performant for the next years, and he was not really involved in the deployment. He don't know what are the impacts for the engineers. So he requests CESAM to make an assessment, to study the project, and to make recommendations. And the recommendation was that since PSA wants to be driven by the services, and since PSA wants to focus in ADAS, autonomous vehicles, to manage the complexity, they must invest in system engineering. The second one was to have clear business objectives. Sometimes we have customers that want to try system engineering to have a look. It can be fine to start to be familiar with, but if we want a company transformation, we need to have clear business objective to justify the deployment of system engineering. In the case of PSA, they have a clear target, reduction of the requirements, 20%, reduction of the test, 10%, and to be sure all the requirements are aligned with the test. So that's very important because even if it seems to be low, 10% of reduction of the test is several million euros saved every year on test. We are talking about 50, 60 million euros saved. Another factor for success is manage the transformation as a middle-out project. So we work with top management, we align the scope, and when it is validated, we move to middle management. We request middle management feedback, we come back to top management, and we do like that till the engineers that are doing the design. And it is important because of that, the company can be aligned in the transformation. Another example, follow and monitor the maturity of the adoption. It seems simple, but again, we are talking about 15,000 people, organization, adopting a new way to work. So it's very important to master how these teams are moving into the new methodologies. One more factor, seems quite simple, is to have a war room. To have a war room to be able to put people together, to align, to discuss, to collaborate, and to help them to adopt. So to finalize, why system engineering? So we explained system engineering is a way of solve complexity systems, and collaboration. And it's a way to solve it that has been proved for 15 years, initially for aerospace and defense, and today we can apply it to many other industries, like automotive, industrial equipment, etc., etc. And the last point is that with this approach, we take in consideration all the stakeholders, the value, and we reduce time to market. Just before finish, explain that when we want to deploy system engineering, we need to check 3 pillars. The first one is about methodology. So this methodology should be adapted to different customers. It is what CESAMS is doing. Another one is people. So it means when we want to deploy massively at company level system engineering, we need to change the organization. And change organization is, it can be not easy, must be managed as a global project. And the last one is the tool, is what Dassault System is providing. So we are providing tools, we are providing service platform, able to provide end-to-end digital continuity, and able to provide collaboration between the teams. But it's only one of the pillars of the adoption of system engineering. If we want to make it successful, we need also methodologies and teams. So just before finish, how to deploy. And how to deploy will depend where you are on the adoption on system engineering. So here we have CESAM's offer for system engineering. And in this offer, we move from discovering what it is to understanding what system engineering can bring as value. Then we can move to implementing. So it's typically, we start to make proof of concept. We start with some different entities to see how it can work. And then the steps 4 and 5 are related to deployment. So we will move to firstly assessment, how to deploy, and finally the deploying phases. And deploy phase is something that can, in PSA, for example, it was 2 years deployment. So it can be quite complex. So depending where you are, we can help to move to the next step. So from my side, that's all. I try to simplify as maximum as possible and gain an excuse from Daniel Kropp to not being here. And thank you very much.